Start in a second. Just testing our sound and everything. And yes, this tool is available on the site. You can go check it out. There are videos. The tool is free. You can go generate music. Lots of fun. Make sure you have a GPU. You might need a GPU. So I'm not sure. I did test it on my laptop. It's just slow. It still works, but just much slower. So you can't move too fast on the screen with your hands. So keep that in mind. It's only JavaScript, only front end, so there's no server in this case. This is what coffee sounds like. Yes, sound should be okay. So there is a description at the bottom how it works. There is a similar tool online called Synth Trails. Go check it out as well. I couldn't actually get it to work. This one should be simple. Just load it. It might ask you for like a camera permission to use, and Bob's your uncle. It's not sending any footage to the cloud, but yeah, I mean, yeah, if you don't trust, if you're overly concerned about privacy, then do not use this. But this is front end, just using your local camera. The footage stays on your own machine, but the quality of the, you know, of how it works will depend on your browser and the computer and the like. And let's jump back to the main site. We also have this EEG to music converter. I don't know if you should I try and convert ECG into music. It's probably be more like a TUF type of stuff. So yeah, don't expect it to do much. There is an ECG signal generator on the side, one that you can actually change things, the BPM from 40 to 140 if you feel like stressed. I don't know why the irrelevant ads on my site. Hopefully it will be, ideally it will be someone, you know, a cardiologist advertising their services. Do you need a surgery or something? Call us. We'll start development in a second. We want to release a bunch of new tools on the site for you to play with and watch some ads. Yeah, this one you can already play with yourself, but we'll have another version that we're currently working on where you play against the robot. And yeah, it's a bit like chess. You stand no chance. But yeah, but we're actually trying to show how it behaves when the noise in the signal is increased. Yeah, so then with increased noise, the robot might not be doing so well anymore, but the human still might, maybe, probably not. What else we got? Some feature extraction, which yeah, we'll need more work on those. Currently it just shows you a difference between these three commonly used detector types: fast, Harris, Shi, Tomasi. You can see for this image how it what it detects. So obviously the fast is not working very well. It's pretty much detecting anything under the sun. Maybe that's what you want. Harris pointing out a few regions that is kind of focusing more on. An obvious addition to this tool will be an ROI selection, a region of interest selection, where you put a square and it finds you know, stuff of interest using that algorithm specifically in a certain region. So let me know if interested. We can work on that. or maybe you already done it, send me the link. And She Thomas is kind of similar to Harris. It's not much difference. The labels are smaller, so it's kind of just looks different, but it's actually might be doing the same. I know it's like missing that point there. I don't know if it's important or not, probably not. And here you can select a different image. What's that? The ischemic stroke. I don't know what the stroke is, but ideally the idea is that it will actually, well, you'll have to help it, because in this case you have a lot of the bone in the image, so it will obviously get confused. Yeah, the Harris just focusing on that bit there. You will actually have to indicate a smaller region of interest, like here or there, or compare the two or something, and it will focus on those. What else we got? We got a bunch of blogs that were written by GPT-4, so beware bot alert. It actually says so in at the bottom of each blog. It says that the images and text were generated using DALL-E E3, a beta version at the time. I don't know if there's a better one now. And GPT-4 via the chat OpenAI. We're actually so I released or trying to release another video. What I'm doing is I'm taking actually the whole transcript. Google transcription works pretty well. I still have to go over it, but it's like 90% there. Obviously it gets sometimes it gets certain terms wrong, HTML, ECG, whatever. So yeah, this is essentially a 2 or 3 hour stream being we essentially reduce it, edit it down to as little, as short as possible, in this case 18 minutes, and then we get GPT to actually give us a summary, timestamps, and a title. I don't know, SEO optimized. And get GPT-4 to do the same. So we'll do a quick comparison. I don't know, maybe that's not and that's actually what we gonna be doing today anyway. So did my stream just go out? No, it's still going. It's just on my, just went out on my phone. Anyway, by the way, those streams meant to be interactive, so that if especially if you have checked the site before, if you checked Bionic Chaos and you have any thoughts, you should have thoughts, otherwise you wouldn't be looking at it at all. Do let me know which tool have you used, how I can improve it, what you absolutely hated about it, so on and so forth. The 4 at the bottom still do not work. We're currently combining fuzzy logic with the ECG game, and that's what the video was about. And if there is no human who likes to interact, I'll have to talk to a robot. Let's go quickly over the what GPT, in this case 3.5 generated. So it's the title it generated for my video. And that's not working, is it? Give me a sec. Where's my sound?
Title: Developing a fuzzy logic-driven ECG game, from coding to gameplay. Description: in this video, I dive deep into the development of a unique ECG game, CardioQuest, which utilizes both fuzzy logic and neural networks for processing and analyzing electrocardiogram, ECG, waveforms. I start by discussing the game's HTML structure and its purpose in teaching ECG waveform identification. Then, I delve into the Python and JavaScript codes that form the backbone of this interactive game. Key highlights include the creation of normal and abnormal ECG waveforms, the game scoring logic, and the integration of a fuzzy logic algorithm in a Python Flask application to analyze these waveforms. The video also covers troubleshooting.
Yeah, whatever. That's what GPT-4 wrote, and then 3.5 gave a different title, building an ECG waveform scoring game with fuzzy logic. It's actually better title. I don't know why GPT-4 always insisting on adding something fancy. We don't need that. So yes, in this case, probably GPT 3.5 will suffice. Hey there, this blah blah blah, walk through development process, creating ECG waveform scoring. Yep, we'll delve into JavaScript. Yeah, that's what we'll be doing today as well. So bear with us. Yeah, potentially the description of GPT 3.5 is kind of simpler, and it's not wrong as well. I did watch the video. I was editing the correcting the caption, the transcript for it that Google generated. Yes, we'll publish this one in a second. Okay, what else we got on the side? So I was saying we are combining fuzzy logic with the ECG game. Let's just open another Visual Studio Code. Yeah, I'm doing the CardioQuest bot. The reason being having it in a separate iteration of Visual Studio Code is the fact that the main difference is that GitHub CoPilot, when you start a new chat and do a workspace, yeah, I can explain the whole workspace, I think. No, now it's looking at a specific code. Yeah, if you do like a workspace, a whole project structure, yeah, it should determine workspace structure, deciding which information to collect, gathering info. Then it will actually give you references. So here it looked at this doesn't work, and we obviously don't need all these copies. We have something wrong with our Git, so we're not currently doing proper version control. But anyway, the workspace function of GitHub Copilot Chat just shows, I don't know why, to look at these three files, actually with, yeah, the test file is not doing much at the moment. It's provided a structure of the project, doesn't have the name, I don't know why. Yeah, it doesn't look great. Yes, these files are copies. Yeah, we have to fix fix that. So currently we actually restructured. What's the name? Refracted a much longer, like a 400 line of code, a Python code, the Flask application, into separate files. So now the Flask application is just essentially just Flask, and then it's importing functions from another two Python files, one called ECG processing and the other one is called fuzzy analysis. So you can guess what are they doing. The ECG processing has a process data function, calculate R peak sharpness, and that makes sense, detecting peaks, calculating intervals. And fuzzy analysis has this very long fuzzy logic analysis function that has all the membership functions in it. So we're currently looking at this. I'll run the thing so you can actually see what is it I'm talking about. Yeah, so this is the main function that plays the game. It's currently got a doing not so well. Even with minimal noise, it's labeling everything as a not normal, abnormal ECG waveform, which is not great. We can still play the game ourselves, assuming you are human. I don't know, let me know if you are. And then the machine using fuzzy logic, which currently works really well. So if I restart the page and reduce the noise, yeah, it got one false alarm because there was an abnormal waveform, and it's labeled it as no, sorry, it was a normal waveform. It's labeled it as abnormal. Therefore, the one false alarm. The human is not paying attention as per usual, so not doing great. So I'm already lagging behind. This one is normal ECG waveform, so I did not click on it. Same again, and I get extra 10 points. There are like 3 normals in a row, which is a bit unusual. 4 normals in a row. It's highly unusual. Okay, that's an abnormal. Yeah, and the bot with no noise is just doing absolutely awesome, as in not making any mistakes. So if unless we add some noise to the mix, the bot will be winning by miles, because the game also becomes faster every 50 points. The speed of the scroll window increases slightly. So once we get to about like 1,000 points or so, it becomes super fast and the human is out the door. Can be resting, just watching the robot doing their job. So far I'm still keeping up kinda. But what I wanted to show you is that if you add a little bit of noise to the system, like now, the robot might start doing mistakes. Yeah, so it's already mislabeling stuff. It's essentially in this case with this minimal amount of noise, it's already labeling everything as abnormal ECG waveform, and it's already got up to 6 false alarms. It's essentially every time you had a normal ECG like here, it's labeling it as not normal, and that's obviously a false alarm. What is called false it's a false negative. Yeah. Oops, I clicked on something that I shouldn't have as well. So the human is not paying attention, and the robot starts making mistakes once you have even a slight noise introduced in the signal. Sorry for that, there's just too much noise outside. I might let the bot do the talking for a bit. I'm also need to protect my vocal cords, but if anyone wants to chat, or even I can even bring you on air if you like. Yesterday we were getting this error that for one of the waveforms, no, that just us starting, that for one of the waveforms we had no fuzzy rule being met, and it throws out this well, it's really a warning, but yeah, it's called an error, but we don't see that anymore because we actually got the GPT-4 to adjust the membership functions for us just slightly, so it doesn't happen. It didn't really know the context. I mean, it did know the context. It didn't know like the specific of what needs to be done. Essentially, we had to go over these membership functions and rules multiple times. So we essentially, I can go over it quickly again, or just get the robot to do it maybe, because I'm losing my voice. Get the robot to do it. Clear. Can any browser show two web pages side by side within the same window? Like two windows within the same browser iteration? Yep.
Absolutely. Some browsers do offer the feature to display web pages side by side within the same window. This is often called split screen or side by side browsing.
Yep.
It's pretty handy for comparing content or multitasking. For instance, modern browsers
just keeps going on stop. Wait. It's probably more of a question for a GPT 3.5 because we don't want to sure someone knows how to do it. Yeah, much quicker as well. How do you do it in Chrome? Yep.
In Chrome, it's super easy. Just follow these steps. Open Chrome and navigate to the first web page you want to view. Open a new tab, Ctrl+T or Command+T on Mac, and go to the second web page. Click and hold on the tab at the second web page. Drag the tab to the left or right edge of the browser window until you see a gray outline appear. Release the tab, and it will snap into place, splitting the window into two. Adjust the divider between the two pages as needed by clicking and dragging it. To exit split screen view, click and hold on the tab divider and drag it back to the edge of the window until the tab snaps back into place. And there you go. You've got two web pages side by side in Chrome. Easy peasy.
That isn't supposed to work on Ubuntu as well? Because it doesn't seem to work for me. Yep.
If you're using Chrome on Ubuntu and the split screen feature isn't working as expected, there might be a couple of things you can try. Update Chrome. Make sure you're using the latest version of Chrome. Sometimes, new features or bug fixes are included in updates that might resolve the issue you're experiencing.
Okay.
Check system settings. Ensure that your system settings.
Meant to stop talking when I say okay. Yeah, I do have add-ons running. No, Edge doesn't seem to do it either. Anyway, let's just go for it. Why is it not the default for clear? Pop those quickly into a different folder. And hide it. Yeah, the test doesn't have much at the moment. We have to rewrite like unit test using unit test library. We might do that later. Clear. Okay, this is the HTML file. We'll eventually need to rewrite the description at the bottom of the page to include all the fuzzy logic machine playing the game description. With the waveform generation JavaScript code, we eventually, not right now, but we would like to add more types of different waveforms with different abnormality levels. If you have any suggestions as to which ones I should include, do let me know. Okay, this is the game logic itself. This is what does, you can explain what it does, but generally it does all the calculation of scores and displaying stuff on the screen. Now, we would like to display everything the fuzzy logic algorithm does. So essentially, on the front page, we would like to show all of this. Now this is the Flask application code, a Python script. We would like to, we already have about 10 or so Flask applications published on our website /server. We would like to add this one as well. Should have some instructions written somewhere as to how to do it quick and easy. Now this is the ECG processing, essentially pre-processing of the data before the fuzzy logic analysis. Just keep in mind, we don't want to do any filtering, so no filtering. We would like the fuzzy logic algorithm to see exactly what the human player sees on the screen. And this is the main Python code that does the fuzzy analysis. If you can briefly explain what it does, that will be great. Keep it short, light. If you want to be funny, if you feel like being funny, go for it, but keep it on the topic of discussion. Also mention unit testing. Yep. Yeah, of course it was. Yeah, so I don't know what happened. It just happened recently, just today. Essentially, that the it kept saying the message you submitted is too long. Please reload the conversation and submit something shorter. So it's quite unusual. Let's pop it into info, because we don't currently have one. Also need requirements in the requirement file as well. So yeah, it's 900 lines of prompt. I thought it can handle it. I'm pretty sure it was able to handle it. I'm not just saying, because essentially originally what was happening is that we were hitting the 40 messages per 3-hour limit all the time. And yes, there was a suggestion somewhere that we should just do longer prompts. Let's control F5 this. Try it again. No. I'm pretty sure something have changed in the model. Let's try 3.5. What's the information bit? So they added that memory component. No, that's different. That's an overlay. Ah, there it is. Yeah, I had that most recent change.
EEG monitor.
Sorry for that. Yeah, I might have to restart the browser or something.
We're testing memory with ChatGPT. Remembering things you discuss across all chats saves you from having to repeat information and makes future conversations more helpful. You're in control of ChatGPT's memory. You can explicitly tell it to remember something, ask it what it remembers, and tell it to forget conversationally or through settings. You can also turn it off entirely. We are rolling out to a small portion of ChatGPT free and plus users this week to learn how useful it is. We will share plans for a broader rollout soon.
Yeah, anyway, not just saying, I'm pretty sure it was working before. Let's try like 500 lines. We'll try this and then do one file at a time. Nope. Okay. Yeah, memory, blah, blah, blah. Don't really understand the point of having those GPTs. They're essentially doing the same stuff as GPT-4 itself can. So what's the point? Okay, let's do them in a different order. So obviously the order will matter. No, okay, let's try the order they're currently being opened in.
Alright, let's break down what we've got here. This HTML document is essentially the backbone of a web page for an interactive game called CardioQuest. The game's main focus is on identifying abnormal electrocardiogram, ECG, patterns.
Okay.
Here's a rundown of the key elements. Metadata and resources. Alright, let's break down your waveforms, JS script. It's quite a comprehensive piece of work for simulating ECG waveforms with some variations. Here's a rundown of the key components and functions. This JavaScript file, Waveforms.js, is a critical component of your CardioQuest ECG game.
Okay.
It's
clear. Yeah, what's the difference between the heading noise? Yeah, don't seem to be much different. Can I not choose one? Clear. 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 I don't know why it doesn't. It just stops working. Anyway, that's the game logic. Clear. Yep. We have clear for clear in the chat window. The text window.
Let's break down what's happening in this JavaScript file for your waveform-based game. It seems pretty complex, so I'll focus on the key aspects. Canvas setup. The script sets up a canvas with specific height and width for drawing elements of the game. Waveform drawing. There's a function draw waveform that draws waveforms on the canvas. The waveform's appearance depends on their type, which is indicated by the color. Score tracking. The game keeps track of the player's score and updates it based on their actions, like hits, false alarms, correct rejections, and misses. It uses different variables, hits, false alarms, correct rejections, misses, for different outcomes. Event handling. The handle click function.
Okay. Clear. Clear. Okay, now we have the Flask app. Can never get me saying Flask. No, now it did. Clear. Yep.
Alright, let's dive into this Flask code which serves as the server side for your ECG waveform analysis game. Flask app initialization. You've got a Flask app set up here, pretty standard stuff. The app equals Flask, __name __, line is initializing your Flask application. Home root. The root is simply returning the index, HTML template. This is probably your game's front end. Analyze waveform root. Now, this, analyze _waveform root is where the main action happens. It's set up to accept post requests, which means it's expecting data to be sent to it, likely the waveform data from your game. Waveform data processing. Inside this root, you're extracting waveform data from the request, JSON, waveform. Then, you're using a function process _data, probably from ECG _processing, to process this waveform data. This function seems to return various ECG parameters like positive peaks, negative peaks, amplitude, etc. Data conversion. Post-processing, you're converting some of the data, like peaks and amplitude, into specific formats, integers or floats. This step seems necessary for the fuzzy logic analysis. Fuzzy logic analysis. Next, you're feeding this converted data to fuzzy _logic _analysis, from fuzzy _analysis. This function is likely where the core of your game's decision-making logic resides, analyzing the ECG data and classifying it as normal or abnormal. Response formation. After analysis, you're forming a JSON response that contains both the raw processed data and the results from the fuzzy logic analysis, including the decision, normal, abnormal, and various membership values, like amplitude membership, positive peaks membership, etc. Error handling. There's a try except block for error handling. If anything goes wrong during the analysis, it catches the exception and returns an error response. Running the app. Finally, you have the typical if __name __equals __main block to run the app. You've set it to debug mode and specified port 5001. Overall, your Flask code seems well structured for handling ECG waveform data, processing it, and using fuzzy logic for analysis. It's a neat implementation for a game that's probably educational and engaging, especially for those interested in biomedical engineering or related fields. Alright, so this is your ECG _processing.py script, focused on analyzing ECG waveform data. Let's break it down. Data preprocessing and peak detection. The process _data function starts by converting the input data to a Numpy array and normalizing it by subtracting 300. It then calculates the median and the median absolute deviation, MAD, of the waveform data. These are used to set a prominence value, which helps in identifying significant peaks in the waveform. For detecting positive peaks, you're using Scipy. Signal. Find underscore peaks with the calculated prominence value and a minimum distance between peaks. For negative peaks, you're looking at the inverted waveform and considering the 95th percentile for height. Amplitude calculation is the difference between the max and min of the waveform, scaled down by 600, and rounded off to 2 decimal places. The calculate underscore R underscore peak underscore sharpness function identifies the R peak in the ECG, the highest point in the waveform, and calculates its sharpness. It does this by finding the width of the peak at its half maximum and using that to calculate a sharpness score. The sharper the peak, the smaller the width, leading to a higher sharpness score. The detect underscore peaks function is an additional peak detection method, where it considers peaks above a certain relative height of the maximum peak. This is probably used for more precise peak detection, necessary for interval calculations. Calculate underscore intervals uses the peaks detected by detect underscore peaks to calculate PR and RT intervals. These intervals are important in ECG analysis as they represent specific electrical activities in the heart. It normalizes these intervals by the total length of the waveform. The function handles different scenarios based on the number of detected peaks, which is crucial as not all ECG waveforms will have a clear set of peaks. Overall, this script appears well constructed for extracting meaningful information from ECG data. It incorporates various signal processing techniques to identify key features in an ECG waveform, like peaks and intervals, which are essential for subsequent analysis, such as the fuzzy logic analysis in your Flask application. The use of normalization and scaling also indicates a focus on making the data more uniform and comparable across different inputs, which is vital in biomedical signal processing. In your fuzz underscore analysis.py script, you're implementing a fuzzy logic system for ECG waveform analysis. It's quite a sophisticated approach to categorize ECG waveforms as normal or abnormal based on various parameters. Here's a breakdown. Fuzzy variables setup. You define fuzzy variables, positive underscore peaks, negative underscore peaks, amplitude, R underscore peak underscore sharpness, PR underscore interval, and RT underscore interval, each with their respective membership functions, too few, normal, too many, etc. These membership functions are defined using triangular membership functions, fuzz, TRMF, which is a standard choice for fuzzy logic systems. Abnormality is your output variable, indicating the likelihood of the waveform being abnormal. This is also categorized into unlikely, possible, and likely. Fuzzy rules. You create a set of rules that define how the input variables relate to the abnormality output. For example, the rule underscore normal states that if all input parameters are within the normal ranges, then the waveform is unlikely to be abnormal. Other rules like rule underscore abnormal underscore amplitude underscore peaks and rule underscore abnormal underscore intervals define conditions under which a waveform is likely to be abnormal. Control system and simulation. You compile these rules into a control system and use this for simulation. The system takes actual data, applies the rules, and computes the outcome. Analysis and decision making. The fuzzy underscore logic underscore analysis function takes in the processed data, inputs it into the fuzzy control system, computes the outcome, and then interprets this outcome to make a decision on whether the waveform is normal or abnormal. The highest membership category, unlikely, possible, likely, is determined for the computed abnormality score, and based on this, a final decision, normal or abnormal, is made. Membership calculations. The calculate underscore memberships function computes how strongly each input data point belongs to the different categories of its corresponding fuzzy variable. This is essential for understanding how each parameter contributed to the final decision. This fuzzy logic approach is quite fitting for ECG analysis, as it mirrors the real-world uncertainty and variability in ECG waveforms. By not relying on hard thresholds but instead using fuzzy rules, your system can potentially handle the nuances of ECG data more effectively. It's a smart way to integrate clinical knowledge into a computational model, and it can be particularly useful for educational tools or preliminary waveform analysis in a clinical setting.
Yeah, I want all this output that we are currently only see in the Python terminal to be shown on the front panel, the front page. So essentially transferred into JavaScript and HTML. So we can see the whole process of what the fuzzy logic algorithm does. Yep.
To display the analysis results from your Python backend, Flask, on the front end, HTML, JavaScript, you need to ensure that the data processed by your Python script is sent back to the client's browser and then rendered appropriately on the page. Here's a step-by-step approach. Send data back from Flask. Your Flask route, analyze_waveform already returns JSON data. Ensure it includes all the necessary information that you want to display. Based on your description, it seems like you want to show the analysis data and process data. In your JavaScript file, when you make a post request to analyze_waveform, you receive this data as a response. You should handle this response to extract the data. Modify the display analysis result function in your JavaScript to update the HTML elements with the data received. You'll need to ensure your HTML has elements, like divs or spans, with appropriate IDs where this data can be displayed. Your HTML should have placeholders where this data will be displayed. Something like. You might want to style these elements in your CSS to make them visually appealing and fit the overall design of your web page. By following these steps, you should be able to display the analysis and process data from your Python backend on your game's front end, allowing users to see the results of the fuzzy logic algorithm in real time.
Okay, do we actually need to display all that? It might become complicated and we might stuff things up. What do we have in a console? Right, we actually are showing it in the console. So that's probably will suffice. Yes, for example, it's showing the membership for Amplitude to be mostly medium. So I reckon that should be enough. So essentially on the front panel you have your analysis result. the number of positive negative peaks, raw amplitude, peak sharpness, R peak sharpness. Well, the R peak is actually assuming the tallest peak in the current waveform. Yes, you can imagine one of the problems with this type of analysis is that we don't have continuous ECG scrolling. We have one PQRST wave coming at a time. So we don't have, for example, the distance between R peaks. We only have a PR interval, which is really messy. Those values are incorrect when there is a noise in the signal. It's essentially finding way too many peaks. That's also why the detection isn't working. Yeah, that's something we have more of an interest fixing. No, so instead of that, yeah, don't worry about that. So what that number is, it doesn't really matter. It's just not zero. So when the noise level is not zero, these two positive and negative peaks are correct. However, this is wrong. I think because it's finding too many peaks. Yeah, I want to go over this. That's the one we want to improve.
Alright, I see what's happening here. You're right to question the PR and RT interval results, especially given the detected peaks. Let's dive into the fuzzy logic and see where it might be going awry. PR and RT intervals. You mentioned that the intervals being too short doesn't align with the number of peaks found. This discrepancy might be rooted in how the fuzzy rules are set up. The script is interpreting these intervals without considering their relation to the number of peaks. In a more realistic biomedical context, these should probably be analyzed in conjunction with each other. Rule modification. To address this, you might need to adjust or add rules that account for the relationship between.
I think it's more to do with how the PR and RT intervals are being calculated. Essentially what's happening is that when we have too many peaks found, in the case of slightly elevated noise, that interval calculation is not actually looking at the correct peaks. The reason I'm mentioning that positive peak and negative peak number is correct is because we actually applying some sort of thresholding or other technique, please check it in the code, that doesn't allow for too many negative and positive peaks being detected. Can you have a look at the code? Yep.
Got it. It sounds like the issue is more about how the PR and RT intervals are being calculated in the context of an elevated noise environment and how this affects peak detection. I can certainly take a look at the code to understand better how these intervals are determined and how the peak detection is being handled. Please upload the relevant portion of your code, focusing on the sections where PR and RT intervals are calculated and where peaks are detected. This will allow me to pinpoint the potential issues and suggest improvements. Alright, let's dive into the code you provided earlier and analyze the key aspects, particularly focusing on the PR and RT interval calculations and the peak detection process, especially in the context of elevated noise. Peak detection with noise thresholding. Your approach involves identifying positive and negative peaks with some form of thresholding. This is a solid method to minimize false positives due to noise. However, it's crucial to ensure that this thresholding is not too restrictive or too lenient, as it can miss real peaks or include noise as peaks. PR and RT interval calculation. The PR and RT intervals are normalized and calculated, but it seems like the issue arises when there are too many peaks due to noise. The algorithm might be incorrectly identifying which peaks to use for these interval calculations. Potential issue. The key problem seems to be the algorithm's inability to correctly identify the relevant peaks for PR and RT interval calculation in noisy conditions. This could be due to how the algorithm distinguishes between true signal peaks and noise-induced peaks. Refine peak detection. Improve the peak detection algorithm to better differentiate between actual heart signal peaks and noise. This could involve more sophisticated thresholding or implementing a different peak detection algorithm. Improve interval calculation logic. Modify the interval calculation to be more robust against noise. For instance, you could implement checks to verify the validity of peaks being used for interval calculations. If the number of detected peaks is abnormally high, the algorithm should reconsider which peaks are used for calculating intervals. Use noise reduction techniques. If noise is a significant issue, consider preprocessing the signal with noise reduction techniques before peak detection and interval calculation. Adaptive thresholding. Consider implementing adaptive thresholding that adjusts based on the noise level of the signal. These are general suggestions. For a more precise solution, I need to see the specific implementation details of your peak detection and interval calculation algorithms. If you have more code snippets related to these parts, please share them for a detailed analysis. Certainly, let's take a closer look at the code you've shared previously and pinpoint specific areas for improvement, especially in relation to the PR and RT interval calculations and peak detection in the context of noise. From the snippets you provided, here's a recap and analysis. Peak detection, positive and negative peaks. You've mentioned that the detection of positive and negative peaks is accurate, suggesting that the thresholding or technique used here is effective. However, we need to ensure that the peaks used for PR and RT interval calculations are correctly identified from these detected peaks. PR and RT interval calculation issue. The main issue seems to be with the PR and RT interval calculations, particularly when the signal is noisy and there are too many peaks detected. This could mean that the algorithm is not correctly identifying the P-wave, QRS complex, and T-wave peaks necessary for these calculations. Code analysis for interval calculation. Interval identification. Look at how the intervals are being identified from the peaks. Are you using the first positive peak as the P-wave and the first negative as the QRS complex, or is there a more complex logic? This identification process might need refinement. Normalization method. The normalization of the intervals might be skewed by the presence of extra peaks. Re-examine the normalization logic to ensure it's robust against noise. Improve peak selection for intervals. Implement a more sophisticated method for selecting the correct peaks for PR and RT interval calculations. This could involve checking the distance between peaks, the amplitude of the peaks, or using a machine learning approach to classify peaks. Noise reduction in preprocessing. If noise is a significant issue, apply a noise reduction filter before peak detection. Alright, having reviewed the ECG_processing.py script, I see several potential areas for refinement. especially in relation to the calculation of PR and RT intervals in the presence of noise or multiple peaks. Peak detection adjustments. Currently, detect_peaks is used in calculate_intervals to identify peaks, which then determine the intervals. The approach seems quite simplistic, considering only the relative height of the peaks. It might be beneficial to incorporate more sophisticated criteria, like the shape or duration of the peaks, to better distinguish between P waves, QRS complexes, and T waves. Intervals calculation logic. The calculate_intervals function assumes the first three peaks represent the relevant points for PR and RT intervals. This assumption might not hold in noisy data or when ectopic beats are present. A more robust method would involve identifying the specific characteristics of P waves, QRS complexes, and T waves. The use of the first two or three peaks might be oversimplified, especially in cases with complex waveforms or arrhythmias. Improvement suggestions. Improved peak identification. Enhance the logic for identifying P waves, QRS complexes, and T waves. For example, use known characteristics of these waves, such as their typical duration, amplitude, and shape. Machine learning techniques could also be utilized for this purpose. Adaptive thresholding. Modify the peak detection algorithm to adaptively set thresholds based on the noise level or variability in the signal. Validation of peaks. Implement a validation step that checks if the detected peaks make sense in the context of a typical ECG waveform. This could involve checking for typical distances between the P wave, QRS complex, and T wave, and their expected amplitudes and shapes. Noise filtering. If noise is significantly impacting the signal, consider implementing a preprocessing step with a noise reduction algorithm, such as a bandpass filter that targets the typical ECG frequency range. Normalization of intervals. The current normalization of intervals based on the total length of the waveform is a good approach, but ensure that this normalization still makes sense in the context of the specific ECG data you're analyzing. Code refactoring. Consider refactoring the code to separate the concerns clearly, one function for peak detection, another for peak validation, and a third for interval calculation. This will make the code more maintainable and easier to debug. By enhancing the peak detection and interval calculation logic, and potentially incorporating more advanced signal processing or machine learning techniques, the algorithm should become more robust against noise and more accurate in determining PR and RT intervals.
So we changed. When we say we, is well, kind of me, just a bit, but mainly GPT-4 and GitHub CoPilot. We need to see a correct rejection. Now those numbers still seem to be too low. Go over this stuff one by one. Trying in a noise condition, those PR intervals are way too low. We'll keep it at 100 because that number should just make sense. So it essentially means that if the noise caused too many peaks to be detected in short succession, they will not be taken into account. Yeah, this code essentially says if there's more than one peak, that code is actually not correct. And I was modifying the wrong bit. It's actually this bit here. So if the number of peaks is more than one, which in this case, yeah, the current problem that we're trying to solve is that these numbers are too low. What these numbers should be is, yeah, if we remove the noise, yeah, those numbers make sense. So 0.4 and 0.3, it's the distance before and after the R peak to the next peak, or if there was no peak to the beginning of the waveform. So those numbers are correct. Problem is when we have noise introduced, those intervals are not being calculated correctly. Yeah, I don't know, GitHub CoPilot again made a suggestion, but not sure what it actually did. It introduces promises, but then it's not actually using it. So we might revert back to the previous code. Well, considering what it suggested, it didn't do much difference at all. Can we go over this code essentially line by line and make suggestions as to how to change it so that when there is a little bit of noise introduced, the PR and RT intervals are still calculated correctly? Currently the numbers are way too small because it's essentially looking at the peaks that are too close that were labeled when there is noise in the waveform. Yep. Yeah, we need to change. a calculate the intervals function. Yeah, there are definitely some issues with the site.
The calculate_intervals function assumes the first 3 peaks represent the relevant points for PR and RT intervals. This assumption might not hold in noisy data or when ectopic beats are present. A more robust method would involve identifying the specific characteristics of P waves, QRS complexes, and T waves. The use of the first 2 or 3 peaks might be oversimplified, especially in cases with complex waveforms or arrhythmias. Improved peak identification. Enhance the logic for identifying P waves, QRS complexes, and T waves. For example, use known characteristics of these waves, such as their typical duration, amplitude, and shape. Machine learning techniques could also be utilized for this purpose. Adaptive thresholding. Modify the peak detection algorithm to adaptively set thresholds based on the noise level or variability in the signal. Validation of peaks. Implement a validation step that checks if the detected peaks make sense in the context of a typical ECG waveform. This could involve checking for typical distances between the P wave, QRS complex, and T wave, and their expected amplitudes and shapes. Noise filtering. If noise is significantly impacting the signal, consider implementing a pre-processing step with a noise reduction algorithm, such as a bandpass filter that targets the typical ECG frequency range.
Okay, that's just how little I know about ECG. I was working with EEG before. But is it just pulling my leg, or there's this Ben-Tompkins algorithm for QRS detection? Algorithm is a real-time QRS detection algorithm. It is widely used for its effectiveness in the ECG signal processing. Here's a simplified version. Okay. Pop it into GPT quickly. Okay, there's something really wrong with the page. It's actually not loading at all. With my internet connection on my internet seems to be fine. By the way, another tool on biocurious that just allows you to, in a simple way, review waveforms. It's a bit heavy because it's sending stuff back and forth to my server. Might close it for a sec. I wanted to check. This code quickly, see if it's an...
Alright, let's break down your pan_Tompkins function, which is clearly set up for ECG signal processing. Bandpass filter, you're using a first-order Butterworth filter. The frequency range you've chosen, 0.5 Hz to 50 Hz, is typical for ECG to eliminate noise outside the heart rate frequencies. Just make sure your sampling_rate is at least twice your highest frequency, Nyquist theorem stuff. Differentiation. This step highlights the slopes in the ECG, basically making the R peaks more pronounced. Using NP, add if 1D is a straightforward way to get the first derivative. Alright, here's what this code does. It's a Python function called pan_Tompkins that takes in a waveform, ECG signal, and its corresponding sampling rate. The function applies the pan-Tompkins algorithm, which is a commonly used method for QRS complex detection in ECG signals. Bandpass filtering. It removes noise from the ECG signal using a Butterworth bandpass filter with cutoff frequencies set at 0.5 Hz and 50 Hz. This step is crucial for removing baseline wander and high-frequency noise. Differentiation. The filtered signal is differentiated using the Numpy function NP, add if 1D. This step enhances the slope of the QRS complex. Squaring. The differentiated signal is squared element-wise, which accentuates the peaks and suppresses the valleys. Moving window integration. The squared signal is integrated over a moving window of 150 milliseconds, determined by 0.150 * sampling_rate. This step emphasizes the QRS complexes by summing up the squared signal within each window. Peak detection. Finally, it detects the R peaks by finding local maxima in the integrated signal using Scipy. Signal. Find_peaks, with a minimum distance between peaks set to sampling_rate, 2.5. This distance criterion helps in avoiding false positives. So, this is a Python script named ECG_processing.py that contains functions for processing ECG, electrocardiogram, data. Let me break it down for you. Processing data, T. The process_data function takes in ECG data, preprocesses it, and calculates various features such as positive peaks, negative peaks, amplitude, R-peak sharpness, PR interval, and RT interval. It calculates the peaks using Scipy.
There's a problem with that code though. I need it in the context of the whole code.
Alright, let's break down our ECG_processing.py code. Data preprocessing, U. You subtract 300 from each data point to normalize the signal.
Yeah, don't worry about it. Yeah, we now have get the detect QRS should in theory be a detect QRS function is not available. However, we do have the pan Tompkins function. Any suggestions would be welcome. Right, it just changed the name there. And calculate the intervals. Everything else is the same. We have that code that might actually work. Well, no, there's an error. Calculate intervals now. Requires 3 input values instead of just the 2. To actually check if that Van Tompkins thing is legit or not.
The Pan-Tompkins algorithm, 1, is commonly used to detect QRS complexes in electrocardiographic signals, ECG. The QRS complex represents the ventricular depolarization and the main spike visible in an ECG signal, see figure. This feature makes it particularly suitable for measuring heart rate, the first way to assess the heart health state. In the first derivation of Einthoven of a physiological heart, the QRS complex is composed by a downward deflection, Q wave, a high upward deflection, R wave, and a final downward deflection, S wave.
So let's have all these magic numbers. Well, at least we know it exists. Why those are not clickable links? Sometimes they are. Once you've seen it, you can unsee it, can you? Now you expect them to be links, but they are not. I wonder if it's just not working properly on Linux. Any chance we can actually remove the sampling rate at all? We're looking at a certain number of data points within a certain waveform. See if it understands. No, we're not concerned with the actual sampling rate. Yeah, we'll get rid of it. And in the band Tompkins, yeah, but don't worry about the sampling rate at the moment. Well, just because, just take my word for it. Trust me, I'm an engineer. What is it they say? Yeah, we still need the window width. But we're getting rid of the sampling rate. Okay, we need another input here, don't we? Yeah, 100 sounds fine. Okay, it's not actually called waveform, it's called the NP data. Oops. Just adding window width there. And the actual number. The frequencies. difference between those two, I don't know. Is this still around this code? Maybe the window width should be larger. Yeah, CoPilot is mostly messing up my stuff. And there's seems to be there is currently something wrong with GPT-4. On the website.
The error message, v cannot be empty, suggests that an empty array or list is being passed to a function that requires a non-empty input. This issue is likely occurring within one of the functions used in the analyze_waveform endpoint. Let's break down potential causes in your ECG_processing.py script. Empty QRS complexes in detect_p_waves and detect_t_waves, the functions. The functions detect_p_waves and detect_t_waves rely on the QRS_complexes array. If the pan_Tompkins function doesn't find any QRS complexes, these arrays will be empty, leading to an empty start and end in the loop, which could cause the error. If the integrated signal in pan_Tompkins is empty, then the R_peaks array will be empty. This could happen if the squared array is empty or the window size is too large. Suggestions for troubleshooting. Check for empty arrays. Before performing operations on arrays like QRS_complexes, p_waves, or t_waves, check if they're empty. If they are, handle the situation appropriately, e.g., by returning a default value or skipping further processing. Validate input data. ensure that the input waveform to pan_Tompkins and other functions is not empty and is appropriately preprocessed. Adjust window size. Verify the window size used in NP, convolve in pan_Tompkins and for detecting P and T waves. An improperly sized window can lead to empty results. Debugging. Add print statements or use a debugger to identify which specific line or function call is causing the error. This can help you pinpoint whether the issue is with peak detection, interval calculations, or elsewhere. Error handling. Implement error handling in functions like detect_P_waves, detect_T_waves, and pan_Tompkins. If an expected array is empty, the function should handle it gracefully, either by returning a default value or raising a custom error message that is more descriptive. Logging. Add logging statements that can alert you when certain conditions, like an empty array being processed, are met. This can be invaluable for diagnosing issues in deployed applications. By systematically checking each part of your signal processing pipeline and implementing these safeguards, you should be able to resolve the "V cannot be empty" error and make your application more robust against varying input data conditions. Certainly. To create a more robust version of your code, I'll focus on adding checks and handling for potential issues that could lead to empty arrays or invalid computations. I'll also streamline the code to make it more efficient and clear. Here's an updated version. Key changes and notes. Empty array checks. Added checks at the beginning of functions to handle empty waveform arrays. This prevents operations on empty arrays which could lead to errors. Returning none or default values. In scenarios where processing cannot be done due to empty arrays, the functions return none or default values. This needs to be handled by the caller function. No major logic changes. The core logic of your functions remains the same. Only additional checks and safeguards have been added. Error handling. The code now has basic error handling for empty arrays. Depending on your application's needs, you might want to add more sophisticated error handling and logging. Remember, this code assumes your input data is formatted correctly and that the processing steps, like filtering, peak detection, etc., are suitable for your specific ECG data. If there are issues with the data itself or with the signal processing parameters, you might need to adjust those aspects as well. Sure, let's refactor your code to ensure it's clean, efficient, and error-free. Here's the revised version. Key changes. Error handling. Added a check at the beginning of calculate_intervals to ensure the waveform is not empty. Window size in pan_Tompkins. Adjusted the window size in the moving window integration step relative to the length of the waveform. This makes the function more adaptable to different waveform lengths. Distance in pan_Tompkins. Adjusted the peak detection distance parameter in relation to the waveform length. Normalization. Normalized PR and RT intervals based on the total length of the waveform. Run this code in a Python environment where Numpy and Scipy are installed. Make sure the input waveform is a valid Numpy array. Remember, the performance and accuracy of this code heavily depend on the characteristics of your input ECG data and the suitability of the pan-Tompkins algorithm for your specific application. To address the issue with incorrect PR and RT interval calculations, we need to refine the detection of P&T waves and ensure that the intervals are calculated correctly based on the positions of these waves and the QRS complexes. Here are some steps to improve the accuracy. Refine P&T wave detection. Ensure that the detect_P_waves and detect_T_waves functions accurately find the P&T waves. These functions currently use a simple maximum value within a window to identify the waves, which might not be accurate in all cases. Consider more sophisticated methods like template matching or machine learning models if your data and resources allow. Check interval calculations. The PR interval is the time from the beginning of the P wave to the beginning of the QRS complex, and the RT interval is from the end of the QRS complex to the end of the T wave. Make sure the intervals are calculated accordingly. Waveform preprocessing. Ensure the waveform is well preprocessed before applying the detection algorithms. This includes filtering and normalizing the waveform. Algorithm parameters. Review and adjust the parameters of the pan-Tompkins algorithm and the window widths used for P&T wave detection to better suit your specific ECG data. Error handling and edge cases. Add checks for cases where P or T waves cannot be Absolutely, focusing on one QRS complex at a time is a good approach, especially for a more precise analysis of the ECG waveform. We'll revise the code to handle each QRS complex individually and then calculate the PR and RT intervals for each QRS complex. This will allow us to deal with cases where the P or T waves are not consistent across different cardiac cycles. Here's how the updated code would look. In this code, we loop through each detected QRS complex. For each QRS complex, we find the closest P wave before it and the closest T wave after it. We then calculate the PR and RT intervals accordingly. This method will provide a set of PR and RT intervals for each QRS complex in the waveform. Remember, this approach assumes that each QRS complex will have a corresponding P and T wave, which may not always be the case in abnormal ECGs. You might need to handle such situations based on your specific requirements. The Pan-Tompkins algorithm applies a series of filters to highlight the frequency content of this rapid heart depolarization and removes the background noise. Then, it squares the signal to amplify the QRS contribution, which makes identifying the QRS complex more straightforward. Finally, it applies adaptive thresholds to detect the peaks of the filtered signal. The algorithm was proposed by Giapo Pan and Willis J. Tompkins in 1985, in the journal IEEE Transactions on Biomedical Engineering. 1. The performance of the method was tested on an annotated arrhythmia database, MIT, VIH, 2, 3, and evaluated also in presence of noise. Pan and Tompkins reported that the 99.3% of QRS complexes was correctly detected. 1. Each fiducial mark is considered as a potential QRS. To reduce the possibility of wrongly selecting a noise peak as a QRS, each peak amplitude is compared to a threshold I, that takes into account the available information about already detected QRS and the noise level. TH of RESH of OLD sub I equals NOISELEVEL sub I plus 0.25 times open. Paran SIG of NA. Sure, let's simplify the code and focus on analyzing individual PQRS complexes without using the Pan-Tompkins algorithm. We'll assume that each waveform represents a single PQRS complex. Here's the modified version. This version of the code simplifies the processing to focus on individual PQRS complexes. It calculates the number of positive and negative peaks, amplitude, R-peak sharpness, PR interval, and RT interval for each waveform independently. We've removed the Pan-Tompkins algorithm and instead used simpler peak detection methods provided by Scipy. Certainly, let's simplify the code and focus on analyzing each QRS complex individually without using the Pan-Tompkins algorithm. We'll process each waveform separately, identifying key features of the QRS complex, and then calculate the PR and RT intervals. Here's a streamlined version of the code. This version of the code is tailored for individual waveforms containing a single QRS complex. It finds the R-peak and then searches for P and T waves within defined windows around the R-peak. The PR and RT intervals are then calculated based on the positions of these waves. Remember, this code assumes the input waveform is a single QRS complex. If your waveform data contains multiple complexes, you'll need to segment it into individual complexes before processing.
Okay, we wanna leave all the code the same and only change the calculate intervals function. So currently, when there is some noise in the signal, the PR and RT intervals are way too small because there's too many peaks being detected.
Got it. So, the main issue you're facing is that noise in the ECG signal is causing too many peaks to be detected, which in turn results in inaccurately small PR and RT intervals. To address this, we need to modify the calculate_intervals function to be more resilient against noise. Here's a strategy we can use. Improve peak detection. We need a more robust way to identify significant peaks. One approach is to increase the prominence or height threshold for peak detection. This can help filter out smaller peaks likely caused by noise. Refine peak classification. Once we've detected peaks, we need a reliable way to classify them as P, QRS, or T waves. This is crucial for accurately calculating PR and RT intervals. Handle noisy data. Implement a strategy to deal with noisy sections of the waveform, like ignoring peaks that are too close together or applying a smoothing filter to the waveform before peak detection. I'm going to modify the calculate_intervals function with these considerations in mind. This is just a starting point. You'll need to refine the criteria in the helper functions, is_P_wave, is_QRS_complex, and is_T_wave, based on your specific ECG data and what you know about the wave characteristics. Also, the parameters for the Savatsky-Golay filter, used for smoothing, might need adjustment depending on your data's sampling rate and noise level.
Can you look at the code again? So in process data function, we do have a median calculation and a prominence value. Are we using it when calculating intervals? Any chance we can move that prominence and median calculation bit of the code and the minimum distance as well? Shall we move it into the detect peaks function so that when we are calculating intervals, it is being taken into account, so we are not looking at too many peaks in the presence of noise? Yep.
Remember to test this updated logic with your ECG data to ensure it behaves as expected, especially in noisy conditions. Fine-tuning these parameters, prominence and minimum distance, might be necessary based on the specific characteristics of the ECG signals you're working with. Absolutely. Absolutely. It makes sense to integrate the prominence and median calculation into the peak detection process, especially when calculating intervals. This will ensure that we're considering the overall characteristics of the signal and not just local features. This approach should help in reducing false positives due to noise. Let's modify the detect_peaks function to incorporate the median and prominence calculations from the process_data function. We also use the minimum distance parameter to further refine the peak detection. Here's how you can adjust the function. Python, copy code def detect_peaks, waveform, min_distance equals 10, hash calculate the median and mad for prominence calculation median_of_waveform equals np, median, waveform, mad equals np, median, np.abs, waveform, median_of_. Hash detect peaks considering prominence and minimum distance peaks, properties equals Scipy, signal, find_peaks, waveform, prominence equals prominence_value, distance equals min_distance. Return peaks, properties. Def calculate_intervals, waveform, peaks, equals detect_peaks, waveform, vr_interval.
Sorry, was the other text-to-speech running? Clear? Okay, so we're moving. Essentially just need to, well, not just, we will stuff up the whole code, but the idea is, currently what's happening is that when there is a noise present in the signal, when there is no noise, it's working fine. When there is some noise present, then the PR and RT intervals are way too low. And this is because it's actually calculating distance between two consecutive peaks that were generated by the noise, and we do not want that. Now the peak detection here, the number of peaks, it's still working fine even if you do have noise, and this is because we're doing this prominence, so we're finding median and doing prominence value of it by multiplying it by 10. So we want to do the same thing so that the detect peaks function is using it. It's not the whole function, is it? It's returning peaks and properties. That should be fine. Then in detect peaks, essentially remains the same, so I'm not sure why it even changed it. Do we need to change the process data function? Remove the median, mad, and prominence value parts of the code. Yep. So in this case,
Yes, you're right. Since we've moved the median, MAD, median absolute deviation, and prominence calculations into the detect_peaks function, we should modify the process_data function to avoid redundancy and maintain clarity in the code. Here's how you can update the process_data function.
wasn't actually used before. Everything else, I suspect, remains the same. Just clear that quickly so we have it getting errors. Clear. Getting errors only some of the time. Right, the PI intervals now seem much better. They even look legit. Yes, you would expect a small variation to it because of the noise present. But those calculations should roughly be the same as when there is no noise in the signal. Still generated a false alarm. That's obviously abnormal. That's fine. Have another abnormal. Now we want to see if for a normal ECG like this, it's still generating 0.6, which is not correct, but at least the PR interval numbers are closer to what they should be, or what they are when there's no noise, and they can just have to make sense, right? Still getting one error in one of the conditions. I have to fix that. You would think this is something CoPilot. Yeah, I keep mentioning. Yeah, I just should stop saying CoPilot or GPT whenever the bot. So the bots are doing something. Go figure. What is it they are doing? It seems like you're getting close to where you need to be with the ECG data processing. Well, yeah, actually we are. Thank you for saying that.
You've noted improvements in the results under noisy conditions, which is great. However, the error you're encountering now, less than not supported between instances of float and none type, suggests that there's a comparison in your code involving a float and a none type, likely due to PR_interval or RT_interval being none.
I just hope that's the one giving me an abnormal result when the ECG wave is obviously normal.
To handle this, you should include a check in your analyze_waveform function, or wherever the comparison is happening, to ensure that both operands in the comparison are not none. Here's a suggestion on how to modify the comparison logic to handle none values gracefully.
Well, how about they won't be none to begin with? So then I don't have to check for it, do I?
This modification will help you avoid the error when one of the intervals is none. Remember, none in your intervals might be indicative of certain conditions in your ECG signal, like a missing peak, so you might want to consider how to interpret these cases in the context of your analysis.
One good thing we can do is actually upload those images. So we have one, the first one is abnormal ECG. And the next one, the second image is normal ECG waveform. that is being misclassified. It's finding an extra negative peak in it. The raw amplitude seems legit, R peak sharpness is okay, PR and RT intervals are fine, but the abnormality score is still too high. I suspect it's because of that negative peak and that comes up as 2 instead of 1, obviously. Yep. Yeah, because if we have 2 negative peaks, the current membership function defines it as being too many. That's why we get abnormal ECG. So if it's a genuine mistake, we can take it. We can make the rules a bit, less stringent. However, we want to just fix it because it should be obvious to the bot that this is one negative peak instead of the 2 that it's counting. And I'm pretty sure if we reduce the noise to 0, it's working fine. So this suggests that the intervals between the peaks are, it keeps saying negative peaks too. Is it always like 1 more than it should be? No, it's 1 in this case, which is correct. That's obviously abnormal. But then it's many times showing 2 when we don't even have a case for 2. So we need to fix that. That should not be happening. So in this case, we should have had just 1 instead of 2. Yeah, we need to fix the negative peak detection. Something is wrong, even if there is no noise in the signal. The first image that I uploaded, it's detecting 2 negative peaks when there should be none. There should be 0. And in the second case, it's still detecting 2 negative peaks when the image clearly shows just 1. And here's the relevant code again.
Alright, I see you've uploaded an image, but unfortunately, I don't have direct access to view it. However, if you can describe the image or let me know what you need to find out about it, I can certainly help you with that. If it's something that requires image analysis, you can simply ask me to process or analyze the image and I can perform various tasks such as object detection, text recognition, or other analyses as needed. Just let me know what you're looking for.
Is this GPT-4? This can't be GPT-4. This is BS. I can't believe it. What on earth? What do you mean you don't have? What? Which LLM model is currently being used? So what? Yes, obviously the GPT-4 can look at the images, but this is why I'm paying for this. Is what's happening there. It's playing and the website is playing up. I don't like it. Can you edit this but not that? Just gives me random errors. Can't do it without the images.
Alright, from what you're describing, it sounds like there's an issue with the peak detection in your ECG signal processing. Specifically, it seems like the algorithm is picking up two negative peaks where there should be fewer or none, which can happen if the parameters for peak detection aren't tuned correctly for your signal's characteristics. Revisit prominence calculation. Look at the prominence value you're using. You're currently setting it to 10*mad. This could be too high or too low depending on your data. You might need to adjust this multiplier. Alright, from what you're describing, it sounds like there's an issue with the peak detection in your ECG signal processing. Specifically, it seems like the algorithm is picking up two negative peaks where there should be fewer or none, which can happen if the parameters for peak detection aren't tuned correctly for your signal's characteristics. The detect_peaks function uses the median absolute deviation, MAD, to set the prominence value for peak detection. This can be quite sensitive to the distribution of your data. If your ECG signals have a different noise profile or if the peaks are not as prominent as expected, the MAD-based prominence could lead to incorrect peak detection. Here's what I suggest. Revisit prominence calculation. Look at the prominence value you're using. You're currently setting it to 10*mad. This could be too high or too low depending on your data. You might need to adjust this multiplier. Check minimum distance. You're using a fixed minimum distance of 10 samples between peaks. If your ECG data has a higher sampling rate, this distance might need to be increased to avoid detecting multiple peaks within one heartbeat. Filtering. It's not clear from your code if any preprocessing like filtering is done before peak detection. If not, applying a bandpass filter to keep only the frequencies of interest could help remove noise that might be causing false peak detection. Visual inspection. If possible, plot the detected peaks on top of your ECG signal to visually inspect where the algorithm is going wrong. Debugging information. It might be helpful to return additional debugging information from your detect_peaks function, like the calculated prominence value and detected peak properties, to understand why certain peaks are being detected. Threshold adjustment. You commented out the relative height thresholding in the original detect_peaks function. Sometimes combining a relative height threshold with prominence can help reduce false positives. Algorithm tuning. It might be that the Scipy signal find_peaks isn't the best fit for your ECG data. You could consider other algorithms or write a custom peak detection based on the specific characteristics of your ECG data. Since you have actual ECG data that the algorithm is misinterpreting, it would be ideal to iterate on these suggestions with that data. If you can visualize where the algorithm is failing and tweak the parameters accordingly, that would probably be the quickest way to a solution. If you want to debug the code with your data here, make sure the data is anonymized and doesn't contain any personal health information.
That's important, isn't it? That's what you care about. It's synthetic data. Don't you worry. Why? You have this one. By the way, these sessions meant to be interactive, but yeah, I'm having trouble with the getting all the messages through. Well, I don't think there's any, but yeah, please try placing comments. Well, first I want to see if they actually technically coming through or not. Okay, so there is one negative peak here, which is correct. Then there is 2 for whatever reason. 2 again. And this one is the same. No, it's the normal, which is also getting 2. And that's why, because of this negative peaks of 2, which is a mistake by the machine, this waveform is being classified as abnormal. It's okay, hopefully you can see these 4 images. The first one is detecting 1 negative peak correctly. However, the other 3, including the last one, which is a normal ECG waveform, for some reason showing 2 negative peaks instead of just 1. Yep. Please don't tell me. Oh, come on.
You've uploaded multiple files with the same name, which might have caused an error in accessing the file. Could you please re-upload the files with distinct names for each? This will help me to access each file properly and provide you with the assistance you need.
Really? They do all have the same name. Well, why not fix the interface? So when you upload files, they have different names. Does that sound like a good idea? Can you try again? Yep. Sorry for that. Come on. Are you kidding? There's something really wrong with GPT-4. Its context got reduced from a gazillion to nothing. And give me specific stuff to my code. If not, I'm not interested. What? Did this CEO get kicked out of the company again? I keep forgetting context. So getting this error as well. Can you give a summary of the whole application, what it does, the code, what files do we have, the name of the files, and how are they structured together in one application? What type of application is it? Yep. Right, we only uploaded the processing pi, which is fine. It's the one we want to modify.
The specific error you're encountering, less than, not supported between instances of float and none type, suggests that your analyze_waveform function expects a float value but receives a none. This could be due to an unhandled exception where a calculation fails and returns none. A variable that is supposed to be initialized with a numeric value isn't set properly before the comparison.
We already have that.
check the analyze_waveform function to ensure all variables used in comparisons are initialized correctly. Implement error handling for cases where calculations might fail and return none. Verify the logic where the comparisons are made, ensuring that you're not trying to compare a value that could potentially be none. Alright, we've got a bit of a situation here with the ECG analysis. The human scorer is not doing great with a score of -90, likely due to a high number of misses and a false alarm. On the flip side, the machine, using fuzzy logic, is outperforming with a score of 50. It's hitting all the marks without any misses, but has raked up a few fuzzy false alarms. The machine's analysis, which is probably based on an algorithm that takes into account various ECG features, concludes the ECG is abnormal. It's considering the number of positive and negative peaks, the raw amplitude, and the sharpness of the R peak. The PR and RT intervals are normalized values, potentially indicating the time between the onset of the P wave and the start of the QRS complex, and the total time from the start of the QRS complex to the end of the T wave, respectively. The abnormality score is a calculated value that probably indicates the degree of deviation from a normal ECG pattern. Given this is greater than 0.5, assuming a threshold between 0 to 1, it's likely why the decision is abnormal. If we're talking next steps or improvements, for the human scorer, it's about training to better recognize abnormal patterns. For the machine, it's tweaking those fuzzy logic parameters to reduce false alarms. Precision matters here, and we've got the data to make it better.
There is a problem with the way the negative peaks are being calculated. In the example image, the number should have been 0. Yep.
Looking at the code snippet you've provided and the image with ECG data and scores, it seems like the issue is with the calculation of negative peaks. If the negative peaks should have been 0 according to the ECG provided, but the fuzzy logic analysis shows 2 negative peaks, then the detection algorithm may not be properly tuned to the data, or there's an issue with the way the algorithm interprets the waveform. In the detect_peaks function, the prominence value is calculated based on a median and MAD, median absolute deviation, approach, which is then multiplied by 10 to get a prominence value for peak detection. If the waveform doesn't actually contain true negative peaks, this could mean that the prominence value being used is too low, leading to the detection of insignificant fluctuations in the signal as peaks. Also, it's important to note that in the context of ECG signals, peaks usually refer to the R peaks, which are positive. Negative deflections are typically referred to as dips or troughs rather than peaks. So, make sure the terminology and the logic used in the code align with the standard ECG interpretations.
Okay, let's split those functions. We'll do a detect tips. Doing the same stuff. If it's doing the same stuff, then what's the point? There's some sort of basic error. Someone is probably screaming at me.
The thresholding and peak detection parameters, such as prominence, threshold, and distance, need to be very carefully chosen based on the characteristics of the ECG signals you're analyzing, and it often requires some trial and error to get these right. Adjust the prominence value used in the detect_peaks function to ensure that it's suitable for detecting only the significant negative deflections in the ECG. Review the preprocessing steps applied to the ECG data before peak detection, e.g., baseline wander removal, noise filtering, to ensure they're not introducing artifacts that could be mistaken for peaks. Confirm that the algorithm's logic for distinguishing between positive and negative deflections is appropriate for the morphology of the ECG waveforms you're analyzing.
Can you generate the code? Yep. That's not what it's called, is it? Find peaks. Fix this. Takes forever. No, no. Cool. So I'll call it now detect negative peaks. So I'll have to separate the functions. That's fine. Don't need that because it's the same as positive peaks. In this case, we need to place that. we have default values, so in theory it should just work. No, it won't. Yeah, we need a better function than this.
In the function detect_negative_peaks, you can adjust the height, distance, and prominence parameters to fine-tune the detection of negative peaks in your ECG data. The height parameter can filter out the peaks that are above a certain negative value. Distance ensures that the peaks are separated by at least that many samples, and prominence defines the required prominence of the peaks.
We need a better function than that, something more similar to detect peaks, but for the detect negative peaks we might use a different prominence value. Would that help? Yep.
If the current prominence value used in detect_peaks isn't suitable for detecting negative peaks, then indeed, adjusting the prominence value for negative peak detection might help. We can modify the detect_negative_peaks function to calculate a separate prominence value based on. If the current prominence value used in detect_peaks isn't suitable for detecting negative peaks, then indeed, adjusting the prominence value for negative peak detection might help.
Is it reading multiple, the same text multiple times? I can't read myself. Like my eyes will get stuffed. I have to use the text-to-speech business. So sorry if it sounds annoying or something.
If the current prominence value used in detect_peaks isn't suitable for detecting negative peaks, then indeed, adjusting the prominence value for negative peak detection might help. We can modify the detect_negative_peaks function to calculate a separate prominence value based on the characteristics of the negative deflections. Since ECG negative deflections may be less pronounced than R peaks, a different scaling factor for the median absolute deviation, MAD, may be more appropriate. Here's an updated version of the function, which includes a different prominence calculation for negative peaks. In this updated function, neg_prominence_factor is a parameter you can tweak. It's multiplied by the MAD to get a prominence value that's specifically tailored for detecting negative peaks. The min_distance parameter is also included to ensure that peaks are not too close to each other, which can be useful to avoid detecting multiple peaks for the same negative deflection. Make sure to test this function with your ECG data and adjust neg_prominence_factor and min_distance as necessary to achieve accurate peak detection. The key is to find a balance that minimizes false positives, detecting something as a peak that isn't really a peak, and false negatives, missing an actual peak.
odd because I don't know where that error is coming from, because I don't actually have that variable anymore. Screaming at me. Can you fix this?
It seems like you're encountering an error when trying to analyze the waveform with the message error in analyze_waveform, peak_height. It seems like you're encountering an error when trying to analyze the waveform with the message error in analyze_waveform, peak_heights. This error typically indicates that there's an issue with the properties dictionary returned by the find_peaks function. It's possible that peak_heights is not a key in the properties dictionary because the height parameter. Make sure to use these functions in your
Something wrong with the text-to-speech.
Make sure that when you call find_peaks, you request peak_heights by including the height parameter. Ensure that properties is correctly accessed and that peak_heights key exists before you try to use it.
But I don't use it.
Here is the corrected detect_peaks and detect_negative_peaks functions.
Can I get a different error? I actually get the calculations. Still gives me 2 negative peaks for when there should be just 1. But now we have 2 separate functions. Make the minimum. Right, there's 1 now, but there was always 1. Should be 1 as well. Go figure. Something silly that I'm doing. is still getting 2 negative peaks being calculated instead just the one, like in the examples in the images I just uploaded. Yep.
If the detect_negative_peaks function is still picking up 2 negative peaks when there should only be 1. If the detect_negative_peaks function is still picking up 2 negative peaks when there should only be 1, as indicated in the example images, the issue may lie in the tuning of the function's parameters. The prominence factor or the minimum distance may not be set optimally for the data you're working with. Here's what you can do to try and resolve this. Adjust the neg_prominence_factor. If the negative peaks are not very prominent, you might need a lower neg_prominence_factor. Increase the _min_distance. Increase the min_distance if the two detected negative peaks are too close to each other and should be considered one peak. Try experimenting with different values for neg_prominence_factor and min_distance. Start with larger changes to see the effect, then fine-tune with smaller adjustments. Try experimenting with different values for neg_prominence_factor and min_distance. Start with larger changes to see the effect, then fine-tune with smaller adjustments. You could also consider visualizing the detected peaks on the waveform to better understand what's happening. Here's an example of how you could visualize the detection with Matplotlib, not part of the ECG_processing.py.
Yeah, this one might stuff up my processing, but we'll give it a go. So these values are default, but then where's the function actually being used over here? Oops. Yeah, it's not actually being used. That's okay. Can leave it as that or put an underscore there. It should not matter. Let's test this again. No, it's still wrong. We'll need to do more troubleshooting. Okay, this will mess up our a Flask application. Should not be doing this. Right, so it's finding 2 peaks here and there. So keep doing it, whatever. Yeah, I knew this will. Yeah, here it's finding 2 peaks. So obviously when they are 0, can I copy? Copy. Obviously, that page will obviously not update. Okay, I think the simplest solution will be just not label anything as negative peak if its Y amplitude is 0. And here's the code again.
Gotcha. You want to skip labeling peaks with 0 amplitude as negative peaks. The solution here is pretty straightforward. You just need. Gotcha. You want to skip labeling peaks with 0 amplitude as negative peaks.
Stuff twice.
The solution here is pretty straightforward.
Clear.
You just need to filter out the peaks
Clear.
that have a 0 amplitude after you detect them.
Clear.
In the detect_negative_peaks function, after. With this modification, the function now only returns peaks that have a non-zero amplitude. This should prevent the issue of labeling a peak with a 0 amplitude as a negative peak. You can test this updated function with your
Is this the full function though? Let's assume so. There's no immediate errors. That's good. It's not working. Yeah, the GUI. Obviously, we'll have this. Why do we do the plotting business? Okay, comment this out. Okay, after a few errors, it's actually running, and it's now indicating the correct number of negative peaks. Yay! No. Oh, come on. Why is it 2 again? Should have been 0 for this. What? Well, okay, because it's not exactly 0. It's let's see if it's working okay when we have no noise. Okay, 1, it's good. Hey, can you explain the prominence factor? How does that work? Yep.
Absolutely. The prominence factor is used to distinguish significant peaks from the noise in the signal. Let's break it down. Prominence in signal processing, especially when analyzing waveforms like ECGs, refers to how much a peak stands out due to its intrinsic height and its location relative to other peaks. A peak's prominence is the vertical distance between the peak and the lowest contour line that doesn't intersect any higher peak. Here's the flow of how the prominence factor is used in your code. Inversion of ECG signal. Since the standard find_peaks function is designed to detect positive peaks, the ECG signal is inverted to make the negative peaks positive for the purpose of detection. Median absolute deviation, MAD. This is a robust statistic to estimate variability. It's used to avoid the influence of outliers that are common in ECG signals. Prominence calculation. The prominence value is calculated by multiplying the MAD by the neg_prominence_ factor. The factor is a multiplier that determines how prominent a peak must be to be considered a true peak. A higher factor means that only peaks that are significantly higher than their surroundings, after inversion, significantly lower in the original signal, are detected. Here's the technical part. For each peak, the algorithm looks for the lowest points on either side of the peak that are either at the same height as the peak or higher. The height difference between the peak and the higher of these 2 points is the prominence of the peak. In summary, by adjusting the neg_prominence_ factor, you're tweaking the sensitivity of the peak detection. A high value means you'll only detect the most prominent peaks, while a low value may include less significant variations in the ECG trace. It's like adjusting the threshold for what you consider true peak versus what is just noise or minor fluctuations. The right value depends on the quality of the ECG signal and the specific analysis goals.
Okay, I know what the problem might be. Hey, here's the code again. We're looking at a specific window size. It's actually working now. I haven't changed anything. You just have to go away, come back. Yeah, the abnormality score for normal ECG before was 0.1, now it's 0.3. That's fine, I think. That's normal again. Let's see when we add noise. That negative peak. Oops. Some sort of weird thing. I can have this as underscore, and they'll actually need those because we have them as default values. Yeah, we'll check what the prominence is. Let's print those quickly. Yeah, I want to filter out the peaks with zero amplitude, obviously, but we also I want to do that as well for a sec. It's still finding that negative peak. That's the problem. Why is that happening? How come it's always the same? It's a bit weird. I don't remember setting it up to do that. Yeah, the GUI outside the main thread will likely to fail, so that's why the plot is not working anymore. Okay, that's unfortunate. I have to comment it out. It seemed to only work the first time around. Can I clear it? Hey, can we clear the plot to begin with? Or the figure? Can we clear the figure before it's being plotted? clearing. Still get that very close to zero negative peak being labeled as a peak, where it should not be. Only the second one in this case should have been labeled. See image attached. Yep.
Alright, from a biomedical engineering standpoint, you're probably getting the near zero negative peak detected because your peak detection criteria might be too sensitive. The threshold or prominence you're setting for negative peaks might be catching even very small fluctuations in a signal. The detect_negative_peaks function uses a neg_prominence_factor multiplied by the median absolute deviation, MAD, to determine what counts as a peak. If the MAD is too low, even noise can be identified as a peak. To fine-tune this, you can increase the neg_prominence_factor to set a higher threshold for what's considered a prominent peak. Adjust the min_distance parameter to ensure the peaks are not too close to each other. This might help to ignore that near zero peak if it's too close to the real negative peak you're interested in. You might also want to look into the baseline noise of your ECG signal. If there's a lot of noise, it could affect peak detection. Implementing a filter to smooth out the signal before peak detection could be beneficial. Remember to tweak the parameters iteratively and check the output each time to home in on the optimal settings.
Yeah, that GUI doesn't work properly. Restart the app. I think that plotting might have stuffed things up. Bloody prominence. Yeah, was the prominence factor should have been larger. All right, that's one. now 0. So I have to fine tune it this way. How is it even possible? Something wrong. Yeah, there's something wrong with that prominence factor. Hey, can we double check the code? The problem with it is if I increase it, then I start getting errors. And if I leave it at 5, at what it is, I get 2 negative peaks when there should be only 1. And here's the code again.
I see what you're dealing with here. When you're working with peak detection, especially on noisy signals like ECGs, setting your prominence factor correctly is critical. Let's run through your code and see where things might be going wrong. Inverting the ECG signal. You're inverting the ECG signal to detect negative peaks, which is a common approach. No issues here. Calculating the median and MAD. You're using the median and median absolute deviation, MAD, to calculate prominence. This is a robust method for noisy data, but it depends heavily on how noisy your data is and the range of your ECG signal. Setting the prominence. You're multiplying the MAD by a factor of 5 to set the prominence. This might be too low or too high, depending on the actual noise level and the peak amplitudes of your ECG signal. If you're getting peaks near 0 that shouldn't be there, it suggests the prominence factor might indeed be too low. Height parameter in find_peaks. You're using a height parameter set to 0 in Scipy, signal, find_peaks. This parameter is intended to set a minimum height for peaks. Since you're working with inverted data, any peak above 0, which would actually be a dip in the original signal, would be considered. This might be why you're catching near 0 peaks as well. Filtering 0 amplitude peaks. After finding the peaks, you're filtering out peaks where the ECG signal is 0. This should theoretically remove flatline data, but if the signal is noisy and there are fluctuations around 0, these would still be considered peaks. Given these points, here's what you can try to adjust. Prominence factor. Increase the neg_prominence_factor until you stop detecting the near 0 peak. If you start getting errors, you may need to look at the specific errors and address them separately. Sometimes, you might need to use a dynamic factor based on the range of your signal. Height parameter. Consider removing the height parameter, or set it to a negative value that reflects the minimum amplitude you would expect from a real negative peak in the inverted signal. Filtering mechanism. Your current filtering might not be enough. You could also apply a threshold based on the expected minimum peak size or other characteristics of a valid peak. Signal preprocessing. Before running peak detection, preprocess your signal with a filter to reduce the noise. You could use a band-pass filter to keep only the frequency components typical for ECG signals. Visual inspection. Plot the detected peaks on top of your inverted ECG signal to visually inspect if the peaks being detected make sense. Iterative approach. Adjust parameters iteratively and test each change to see how it affects peak detection. Let's try adjusting the code with a higher prominence factor and see if that helps. I'll also remove the height parameter for now. If you can upload the ECG data, I could run the updated function and see how it performs.
No, don't do that. First, we need to reduce the number of numbers after the decimal point. Because obviously this calculation is too heavy for anyone to manage. Then why the provenance factor doesn't just work. Let's remove that printing for a sec. Yeah, I think I know what the problem is. I want to use a percentage of mean max. I think we need to replace median with something else. Probably not mean, but maybe it should be, we should be using the absolute distance between minimum and maximum, between maximum and minimum. Or whatever, if you can make any suggestions, that would be great. Essentially, the problem is that we are getting the measurement for negative peaks incorrect. It's giving us 2 peaks when there should be just 1. Okay, I think we just fixed it by increasing the minimum distance to 1000. So it actually works now with minimum noise. Get 0.3159 for normal ECG as an abnormality score. It seems to be working correctly now, but any suggestions as to how to improve the code are more than welcome. Yep. Yeah. we've reached the cap. That's why I was originally trying to put in longer prompts so we don't hit the limit. It's just annoying. Actually thinking stopping paying for it. It's kind of the problem is that it's inconsistent. So I get what it's doing. Yeah, I can handle hallucinations or whatever. Well, hallucinations are actually sometimes considered creativity. When someone hallucinates, they might be thought by someone else as being creative. So that's a highly subjective whatever thing. I'm just annoyed by the user interface, like that limit, the 40 messages per 3 hours. Probably should start try using the API instead. See in terms of cost what difference does it make, but then you don't get access to DALL-E. Like, I mean, it will be separate, and I think those prompts are very expensive. Can we pop this into... Obviously this would not work. Yes, that's what I thought. Yeah, like things like this. I mean, it's a paid service. I mean, like, come on. There's just something wrong on this site as well. Control 5, 3.5. Can you handle a long prompt like this?
It seems like you're dealing with some issues regarding detecting negative peaks in your ECG signal processing code. If you're experiencing problems with multiple peaks being detected instead of just one, tweaking the parameters like the minimum distance can indeed help. Here are a few suggestions and considerations. Median replacement. You mentioned replacing the median calculation with something else. Instead of the median, you could consider using the absolute difference between the maximum and minimum values in the waveform to derive a measure of variability or baseline noise level. Parameter tuning. Adjusting parameters like the minimum distance can significantly affect peak detection. Increasing the minimum distance can indeed help in distinguishing individual peaks, especially in noisy signals. Noise reduction. Consider pre-processing steps for noise reduction before peak detection. Techniques like filtering or baseline correction could potentially improve peak detection accuracy. Evaluation. Continuously evaluate the performance of your peak detection algorithm on various types of ECG signals, including normal and abnormal ones, to ensure its robustness and reliability. Optimization. Look for opportunities to optimize your code for efficiency without compromising accuracy. This could involve refining algorithms, reducing redundant calculations, or leveraging parallel processing if applicable. Documentation and testing. Ensure thorough documentation of your code and conduct comprehensive testing with different datasets to validate its functionality and performance under various conditions. By iteratively refining your peak detection algorithm and considering these suggestions, you can enhance the accuracy and reliability of your ECG signal processing code. If you encounter any specific challenges or need further assistance with implementation, feel free to ask.
Right, it did one error there, but was doing okay until now. And then it generated two errors, almost one after the other. So now back to GPT 3.5.
It looks like you're encountering some errors and issues while analyzing waveform data, particularly related to peak detection and subsequent processing steps. Here's a breakdown of the observations and potential suggestions for improvement. Negative peaks detection. The current implementation seems to have issues with detecting negative peaks accurately, as indicated by the inconsistent results in the number of negative peaks detected. Tweaking parameters like the minimum distance and prominence value can help refine the peak detection process. Increasing the minimum distance, as you mentioned, might alleviate the problem of multiple peaks being detected. Error handling. There are instances where errors occur during the analysis due to unexpected conditions, such as when certain intervals cannot be calculated. Implementing robust error handling mechanisms, such as checking for none values and handling them appropriately, can prevent such errors from causing the analysis to fail. Parameter tuning and optimization. Continuously fine-tuning parameters like the prominence value, minimum distance, and other parameters specific to peak detection algorithms can lead to better results. Additionally, optimizing the algorithm for efficiency, especially if dealing with large datasets or real-time processing, is crucial for improving overall performance. Membership function issues. It seems like there are issues with calculating membership values, possibly due to sparse data or unexpected input ranges. Reviewing the membership function definitions and ensuring that they cover a sufficient range of input values can help improve the accuracy of the decision-making process. Data quality and validation. Regularly validate the analysis results against ground truth data or expert annotations to ensure the accuracy and reliability of the analysis algorithm. Additionally, inspecting the input waveform data for anomalies or artifacts that could affect the analysis results is essential. Feedback loop. Establishing a feedback loop where analysis results are reviewed and any discrepancies or errors are addressed can help iteratively improve the analysis algorithm over time. By addressing these points and iteratively refining the waveform analysis algorithm, you can enhance its accuracy and reliability for various types of ECG signals. If you need further assistance or specific guidance on any aspect of the analysis process, feel free to ask.
Okay, so the good news is that it's now, oops, yeah, shouldn't have clicked on that. That the machine, the board, the fuzzy logic algorithm is now doing better even when there's noise present. So that would be a correct rejection there, and this would be, oh, that shouldn't have been normal. And now all of a sudden it keeps giving errors. Yeah, we have to, so we're trying to improve it when working with noise as well. So when there is no noise, it's kind of no-brainer. It's doing really well. So that's abnormal, that's correct. That should be normal, that's correct. And abnormality score of 0.3. Pretty sure it used to be lower for normal ECG. But 0.3 is okay, as long as it's not going above 0.33 or something. 0.31, that's correct. So that's working okay for when there's no noise. Now question is, what happens when we add some noise to the mix? And straight away, yeah, we're getting this 0.32. It's being classified as abnormal. So it's essentially sitting there on the threshold of being normal or abnormal. Yeah, because that value is way too close to a third. So that's a problem. Yeah, and that one that had the missing negative peak was also misclassified. Yeah. So we will, yeah, we'll probably release this tool for you to play with, even though there's some obvious problems. That's just the way it is, especially when noise is present in the signal. So that's kind of what we're trying to show anyway. Yeah, this one, this negative peak there should have been 0. Negative peak there should have been 0. And it's still indicated 1. That's not good. Someone's asking what kind of waves are these. I'm learning about the Fourier series. We do have FFT. Do we have FFT? We should not have FFT. In this case, we would have it in another tool on the website. Yes, so go check out biomedical.com. This is for all these general questions that what the answer would be. Unfortunately or fortunately, we have, go study at, I don't know what the ad was, it's not sponsored by that university. Yeah, we kind of don't have a tool specifically covering FFT, but FFT is everywhere, so there would be FFT somewhere in there. We do have some real, so a lot of it is synthetic waveforms that you can check out. Everything you need to know about synthetic waveforms. We also have real waveforms. So this is, there will be FFT in here for sure. This is the EEG data in time frequency domain. And go buy, was it a Whoop? No, don't buy the Whoop. I didn't. I heard someone. I mean, it's probably fine. I have one of those breaking as well. I can't talk to it. Like, I mean, it's still working, but I can't connect to it using my phone. Well, by the way, we'll be finishing in 6 minutes. So if you have any more questions, now it's a good time. The 6 minutes is because we're reaching a 4-hour mark, and LinkedIn doesn't allow streams longer than 4 hours, so it's forcing me a break. Same as GPT-4, that's forcing me a break as well. I know it's working again.
Great. It sounds like you've managed to solve the immediate issue with detecting negative peaks in the ECG signal by adjusting the minimum distance parameter. This is a common approach in signal processing. Tweaking parameters like minimum peak distance can significantly improve the performance of peak detection algorithms, especially for noisy or complex signals. Now, about your initial concern regarding the use of median, it's a valid point. The median is robust against outliers and is often used in signal processing to provide a more stable central tendency measure than the mean. However, in your specific context, considering the full range of the signal might be more informative. Here are a few suggestions.
Yeah, it's actually not, I don't know why it's refusing. Sometimes it's keen on generating code. Other times it's like not generating any whatsoever. And I keep asking it to either generate code or write prompts for GitHub CoPilot to do it, but it forgets, like now. Anyway, so this tool on the side will definitely have an FFT in it, and there's the same tool that actually can turn this stuff into music. So it's essentially the same tool, but you also have an option to listen to the waveform. So yes, there will be lots of FFT there, processing that stuff. There's Hova, I think, if I'm pronouncing it correctly. I was asking if I'm doing this again. Yeah, you can look at the YouTube channel, especially the live streams. We are pretty much live streaming daily. So, and yes, some of the live streams will eventually, if something interesting happen, especially if you want to come live or something, ask questions, we can definitely arrange that with probably using Zoom. So we can make better content more engaging. And then I normally turn anything that was interesting in the live stream into a standalone video. So that's what the videos are on YouTube at the moment. And yeah, live stream pretty much daily, hopefully not for 4 hours anymore. And Go check out the site. I don't know if this will work. Might. Ah, yeah. No, I can tell you came from YouTube. We have some people watching on LinkedIn as well, probably contacts, but they don't want to talk. Yeah, and we have a lot of other content coming up, mainly around EEG, but ECG as well, as you can tell, and potentially getting data of wearables and things. See what we can do with that. This one's like a clinical, medical grade stuff, but I can't talk to it. I think it just can be tossed in the rubbish bin. But there is a lot of data sets that we are looking at online. We have some downloaded data already, open source data sets. If you have any that you know about and you want me to look at, or if you have your own data, pop it up on GitHub or any open source stuff. I don't want to deal with lawyers later, and I'm happy to have a look at it. Probably live stream, like a first impression stuff. So beware. Yeah, and my web page RPM at the moment is quite high, so it's a good time to go check the website. You'll be supporting this project. What else we've got? Yeah, all the tools on the page, they need updating. These 4 do not work at all. Currently, we'll be releasing one that's a irrelevant ad. We'll be releasing one that combining fuzzy logic and this game. Where's the game? This one, ECG game. So that's what we're currently doing. Hopefully, if it actually starts working, it kind of works. Yeah, just modifying a few things, and we'll be releasing on the side, so you can play against the machine. I think my LinkedIn stream will go out because they actually don't want you to stream over 4 hours. Or is it still going? I don't know. Yeah, I mean there's a delay as well. There's quite a long delay. No, they did stop it. Fuzzy logic is set theory. I don't know what do you mean by set theory, but can you give a quick overview of fuzzy logic? How is it related to set theory? I don't think it's set theory. It's like a signal detection theory, maybe. Is that what you mean? And can you also give an overview of what we did today? No, you wouldn't know, would you? Because we restarted the thing several times. But we'll give it a go. Yep. Yeah, don't want it to talk. It's annoying, isn't it, when the robot is talking? I just can't read myself, but I'll find a bit on fuzzy logic and set theory, maybe. Yeah, this one.
For fuzzy logic, it's not directly related to set theory in the traditional sense. Fuzzy logic is more about dealing with reasoning that is approximate rather than fixed and exact. In classical logic, a statement is either true or false, but fuzzy logic allows for degrees of truth. This can be incredibly useful in signal processing where you're dealing with ambiguous, noisy, or incomplete data. Fuzzy logic helps in making decisions based on imprecise information, which could be beneficial in interpreting ECG data, where the signal can vary significantly between individuals and even within the same individual under different conditions. In the context of your ECG processing, you might use fuzzy logic to classify segments of the ECG waveform or to make decisions about what constitutes a peak under varying conditions. It adds a layer of flexibility to your signal processing algorithms, allowing them to be more adaptive and robust in the face of real-world signal variability.
Anyway, it's meant to be explainable AI, explainable machine learning. In Python, it's fairly straightforward. There's a Python library for it that anyone can use. It's called SkFuzzy. And Bob's your uncle. Essentially, you need to design your membership functions. Clear. Yeah, design those membership functions, which we do here. We do this for multiple parameters. So in this ECG waveform, this is synthetic waveform. You know, the bot keeps telling me, oh, be careful with publishing personal information, whatever. It's synthetic, it's no one's ECG. So we're looking at the number of positive and negative peaks. In this case, 2 and 1. Then look at the amplitude. It's the amplitude is calibrated, normalized between 0 and 1. We'll look at R peak sharpness. So in theory, it's finding R peak. It's a simple algorithm, nothing like nothing like this Penn-Tompkins algorithm and stuff. I didn't use it because I think it's assuming you have multiple continuous waveform, whereas we only have one of those ECG beats coming once at a time. So it's kind of different. So I don't know how that algorithm probably would not work. Then we so for the sharpness, 0.42 for this one, 0.4 for that one, and we have another example which should be like 0.1 or so like less sharp. You can, by the way, already can go play this game. It's available for you. It's just you'll be playing against yourself, not against the machine. Because we haven't published this yet. Hopefully, we'll publish it this week. So we can place more ads on the website. No, just joking. Anyway, we're looking at that R peak sharpness. Oh, where is it? Yeah, most of them are 0.42, and one of them should be different. That's all that you will see. It's nothing fancy. You will enjoy the ads. Yeah. Hopefully this shouldn't be too intrusive. There's just one banner ad at the bottom of the page. Yeah, there really should not be any ads for the the bottom tools there because they still they don't work well or don't work at all. Like say for example, yeah, what were you asking about the FFT? Yeah, I'm not sure about FFT, but you also will probably learn about statistics and stuff. So there was this statistical tool that talks about entropy, skewness, kurtosis, things like that I used in EEG signals. And all that left from that is this YouTube video, because originally I was programming in LabVIEW, Matlab. I don't do that anymore because the license is too expensive. I mean, if LabVIEW and Matlab want to sponsor this channel, I can go back, use it again, but currently don't have money to pay for the license, so using anything open source. So all that left from this tool currently doesn't work, and all that left is a broken tool and a bunch of YouTube videos that people for some reason still watch even though the tool is not working. So that's fine, but currently I'll essentially be redoing something similar. So it's a statistical analysis a toolkit in LabVIEW. Obviously Python will have something similar, so we're now recoding the whole thing. Not me, GPT-4 is recording this for me. Yeah, so hopefully, I don't know if, yeah, some of those ads are not relevant anyway, so just get rid of them. I mean, obviously you can use a ad blocker. I have one as an add-on on Firefox, works perfectly well. You won't see any ads whatsoever on any page, but then keep in mind that you might also not see any content in the future if that content creator is relying on the advertisement revenue. I do not, but it would be nice. So I like ads. No one likes ads, but everything is an ad. Then when you talk, you promote yourself. Anyway, yeah, there's a bunch of tools that will need some more work. Yeah, there probably would have been much FFT in this one as well. It's a cross coherence between two channels and showing you power spectral density for, can select, this is 16 channel data, so you can select your channel, do detrending. I'll show you coherence value, so essentially how similar or different the two channels are. And yes, there will be FFT somewhere in the processing of this data. And yeah, this tool doesn't look great. We'll have to redo it. Yeah, this peak here in coherence essentially shows that at that specific frequency there is something going on between the two channels. You can't really see it from the time series. You can't really see it from the power spectral density, but you can see it in the cross coherence function. So essentially, if this peak is really high, you know to go look at that frequency, and there is something going on there. And this probably this data is seizure, epileptic seizure, so EEG while the subject having a seizure. So if you have any strong correlation between the two channels, which can be measured as cross coherence between the two, then you know potentially that the seizure is just happening at both channels at the same time. And you can see how it changes when you increase the time window. Yeah, there's something happening at that frequency. So it essentially could be used for seizure detection or something. Yeah, this is where I'm using a lot of electricity because I should limit the window size there. Okay, it gets stuck. That's the kind of stuff I need to fix. So yeah, this was probably from a year ago. I have to go back, revisit it. The what's higher on the page been developed more recently, so probably will work better as well. Well, I might just sign out unless there is a check. I'm streaming on Twitch, no questions. LinkedIn just dropped me out because the 4-hour limit, and YouTube. We had a bunch of questions, but they were not quite technical, were they? Yes, we discussed fuzzy logic and what kind of waveforms and FFT maybe. Yeah, there will be a lot of content on YouTube on FFT. I don't want to add to that. It's probably a saturated you know, content area anyway. So I didn't have my lunch yet, and it's already 5 o'clock. So I'll see you probably tomorrow, maybe. Bye.